Okay, so last time we started uh, talking about how to calculate the optic flow. Okay, maybe I should back up a little bit and kind of remind you what we were doing. We said that we are after this motion field estimation. Okay, motion field is, if you remember, it is the projection of the motion vectors on the image frame or the image plane. We said that estimating the motion field directly is not that easy. We can't do it. Instead, we are going to do this. We are going to estimate the motion of the brightness patterns, and we are going to call that optical flow. Optical flow basically means that you find a pattern of brightness, and you try to track it between the frames. Yeah, so you will say that this pattern moved this direction, and this direction. So direction plus the magnitude of the motion. That's the optic flow, and for that we will assume that brightness of the moving object doesn't change. So we have this brightness constancy equation. If a point P is moving in the three-dimensional space, and if this is xt, yt, and zt is coordinates in the real world, okay, then we will assume that whatever the projection of this point on my image frame, okay, will have a constant intensity, because wherever you move your object in the scene in time, its brightness will not change. That's our assumption is. So if this function E xt yt t is the function that tracks our objects, then this function as it is will not change its value. So if I take the derivative of this function with respect to t, it should be a constant value. So if you take the constant value derivative, it should be 0. So we are going to take the derivative of this function, and we are going to say that derivative should be equal to 0. But this function has other function that depends on, okay, on t. So there is xt and yt and t itself. So we have to use our common knowledge about the calculus. This is how you take the derivative of this function. So take the function. Okay, first of all, I need to take the derivative of this function with respect to t, that's this one. Also take the function, the derivative of this function with respect to y and x, and then multiply those, the derivative of those y and x with respect to t. Okay, that's how we learned about the taking this kind of functions of derivatives, the chain rule, and this is what we do. So the resulting equation after taking the derivatives is this, and when I look at this equation, I see many things that I know. For example, this one is derivative of the image with respect to x dimension, derivative of the image along the y dimension, x and y dimension, derivative of the image along the time dimension. I can easily calculate this one and this one and this one. We have been calculating these two many times, right, for the edge detection, corner detection, etc. Now, since we are talking about motion, I can definitely calculate this one too. Okay, those are the three things that I can calculate, and these two things are the things that I like to calculate actually. I mean, the speed of this, what is this? Derivative of x with respect to t means that it is vx, speed of velocity of something, velocity of the moving pattern in x dimension, and the velocity of the moving pattern in the y dimension, right? So I need to know these two. I can calculate these three. Okay, these three. So what am I gonna do? I will put these in an equation, but the thing is that I have two unknowns and one equation. That's the problem. For a given pixel, this brightness constancy equation only gives me just one equation, but I need two unknowns. So what am I calculating here? I have a gradient vector. This is the gradient vector. This is the velocity vector. Okay. So I am taking the dot product of gradient vector and the velocity vector, and I am adding it with a scalar, and I'm getting a 0. So if I am lucky, that's what I am saying. If I am lucky, if the direction of the velocity vector is the same of the gradient vector, then I can definitely find my velocity vector, because I mean velocity vector has two components. One is the magnitude of the velocity, the other one is the direction. If the direction is the same as this one, then I will get this magnitude. That's no problem. But if it is not, then I am not going to find the velocity of the moving pattern. The thing is that even the worst thing is this: if my objects, let's say, if this is my object, okay, and if my object is moving this direction, okay, that's my velocity vector, and this is my gradient direction, right? If I multiply this gradient direction, okay, with the velocity direction, then I get a 0, right? These are perpendicular. So in that case, this equation will not give me anything. Okay? In that case, this equation will not give me anything, because I am getting a 0 from here. Okay? And this one has to be 0 in that case. What does that mean? It means this. If you look at only this part of the image, and if my object is moving in this direction, I know that my gradient direction is this. You won't be able to observe any motion, right? You won't be able to observe any motion. That's what the equation says, and that's what our intuition says too. That's called, this one is called aperture problem. Okay, aperture problem. And the aperture problem says that if you look at your scene through a very small aperture like this one, okay, let's make this even smaller like this one. If you look at your scene through a small aperture like this one, and if your gradient is perpendicular to the velocity direction, then this brightness constancy equation will not give you anything. But if you are lucky, okay, and if you're, let me draw the okay, this is my velocity vector. Okay, if my velocity vector is this way too, then I can see the motion, right? Okay, then I can see the motion, and I can get the motion vector exactly as it is. Okay, so it is kind of how lucky you are, or maybe we can do this, we can say that I won't be able to give you the velocity vector for this kind of a case, but what if I am looking at an aperture like this? In that case, doesn't matter what my let me make this a little bit like this, okay? Doesn't matter what my okay, doesn't matter what my velocity vector is. It could be this way, or it could be this way, or it could be this way. Okay, I can see the motion because I have gradient vectors this way, this way, this way, this way, and this way, in this part of the image, in this aperture. Okay, so in this case, I can calculate the optic flow because I have components. So it's look like, what does that mean? It means that For a given patch, image patch, if you can find a corner, that means that you can solve the optic flow problem there. If you cannot find the corner, then you won't be able to find the optic flow. That's what the aperture problem says. Intuitively, it looks that way, and our algorithms are going to do the same thing too. So we have this one. This one says that. This one says that. Okay. If you multiply your velocity vector with the image gradient and add the time gradient of your image to three-dimensional video sequence, you are going to get 0. Okay, you can get the exact value of V only if you are looking at the right image patch and and we talked about this, and we said that we are going to use this algorithm. We are going to take a 5 by 5 window like this one. Okay, 5 by 5 window. For each pixel, I am going to calculate the image gradient. Also, I am going to calculate the derivative of the image with respect to time for each pixel. And if I add them, if I multiply this with V, that is the pattern velocity, image pattern velocity. If I multiply it with V, add it with T, I should get a 0. But due to errors and that kind of stuff, I said it's an epsilon. Okay, that's an error. If I write this equation 25 times, one after the other, so that means what? Because I have 25 pixels in there, right? I will have 25 equations and 2 unknowns, because I am assuming that all of these pixels are moving in the same direction. That's my assumption is. So I will get many equations with just 2 unknowns. Then let's write these equations then. This is what I am doing, okay? So write it. Remember this was equal to 0, then the other side is minus ET, okay? First equation, and this is the 25th equation, okay? And this is the linear case, okay? So 2 numbers here, 2 numbers there, total of 25 numbers here, just 2 unknowns, and 25 numbers in there too. So this is a 25 2 matrix, 2 by 1 vector, 25 by 1 vector. Okay. If I do it this way, if I solve it, then I should get this 2 by 1. But I mean, having this kind of an equation set A times V equals to B doesn't mean that I can always solve it, because A is not a rectangle. A is not a square matrix, right? So I am using this trick. I multiply A with AT times A makes it a square. A is 25 by 2, right? So this is 2 by 25. So 2 by 25 times 25 by 2 makes a 2 by 2 matrix, right? So it's a square. So of course I multiply the other side with AT2, and I take the inverse of this ATA and multiply both sides by it, and I get my V. Okay, so it is ATA minus 1 times AT times V is my solution. But the thing is that this one has to be invertible. This 2 by 2 matrix has to be invertible. Let's see what kind of a matrix we have in there. Okay, let's see what kind of this is A. Okay, if I multiply A by AT, as we have seen last time, I get this 2 by 2 nice matrix, and this is something we are familiar with. This is exactly the same matrix that we have solved for corner detection. We said that get this matrix if it has 2 singular values with the two eigenvalues, then we said that this would have been there would have been a corner in it. If there is one, there is an edge. If there is no eigenvalue, it's all 0. Then that means that it's a flat region. To invert a matrix, okay, it has to be rank of 2. It has to have, for a 2 by 2 matrix, it has to have 2 eigenvalues. If this one has 2 eigenvalues, then I can invert it. That means what? if my original 5 by 5 window has a corresponding matrix has two eigenvalues, then I can find the optic flow vector. Otherwise, I can't. Okay. So our intuition is correct. Our equations reflect our intuition. So that's nice. So that's our algorithm. Okay, that's our algorithm. Okay. So I think we stopped at this point last time. Let's continue from this point. Let me give you the whole algorithm. They give you n image frames from E1 to En. Okay. Maybe I shouldn't call these E's, but maybe I should call these I1 to In, because the E is the whole thing, right? I mean, this is my E, three-dimensional, okay, and inside E I have many frames. Okay, this is this whole E. This is I1, I2, up to In. Okay. So they give you this image sequence from I0, I1 to In, and if I put them together, I get this three-dimensional space E, and N is the dimension of the. And now I'm going to pick. Now I'm going to pick, like, when am I going to calculate these optic flow vectors? I will say that I am going to calculate it for 5 by 5 image patches for all the E space. Okay, for each 5 by 5 patch, I am going to calculate it. So in this case, I accepted n by as 5. It could be like 3 or 7 or 9, usually odd numbers. Then I will pick two standard deviation numbers for smoothing, sigma s and sigma t. S is for spatial. Okay, it comes from the space. So this is space, this is spatial. Okay, so this is spatial smoothing. Okay, sigma s for space. For each image, I am going to use this sigma s to smooth our image. Then I will smooth my data along the time dimension too. So there is a sigma t2, time dimension, space dimension. Okay. So sometimes we call these kind of spaces spatiotemporal. Okay, both space and time, spatiotemporal spaces.
So what is the meaning of filtering? What spatial filter? Yeah, I mean, when we apply the filter, we lost some details. So
whatever we have been doing up to now, they are all called spatial filters.
I got it.
Okay, so if you have, I mean, this is x and y, right? Yeah. X, y. This is all about space. So your Gauss smoothing filters that you have applied so far are all spatial filters. If you try to apply your filters along this dimension and this one, then they become temporal filters. Okay? This is in 3D, but this is not our 3D world, okay? This is space, two-dimensional space plus one-dimensional time space. If you like to extend it a little bit more, you can get a four-dimensional spaces, three-dimensional spatial space plus one-dimensional time space. It is 4 dimensions. As you know, I mean, dimensions are something that we make up, right? I mean, as humans, our brains can grasp our outside world using this kind of a modeling. Some kind of a crazy physics professor can come up with 7-dimensional world model, and he says that if you represent your model in this 7-dimensional model, then you can explain this and this. Remember, when we represented our 2-dimensional or 3-dimensional real world coordinates with 3-dimensional 4-dimensional vectors, that made lots of things possible for us, right? You remember that? It is like that. I mean, if you are smart enough, you can invent your own space representation for the real world phenomena explanation, and you call it 4-dimensional, 5-dimensional, 6-dimensional, whatever. But I mean, our real world around us, it just continues without us too, right? I mean, it doesn't need our modeling of the world as 2-dimensional, 3-dimensional. These are just made up stuff. I mean, if somebody asks you how many dimensions are in the world, and you say, it depends on what kind of theory you are using, right? That doesn't mean, I mean, if I think my world as 3-dimensional, that doesn't mean that I am doing wrong. Why? Because there are many things that I can do with this model. That model is useful for many, many things. As an engineer, I can use it. If I represent my world with 4 dimensions, 5 dimensions, 6 dimensions, if some useful stuff is coming out of it, then that's useful. That doesn't make my world outside world 4-dimensional or 5-dimensional. The world doesn't need me to operate as it is. It just operates as it is. Okay? Good. Okay, so this is a 3-dimensional representation of image plus time stuff. Okay, so I am going to use two smoothing. One is for the XY smoothing, sigma s. One is for the sigma t for the time dimension smoothing. Typically, 1.4 pixels is the width of the smoothing kernel, and sigma is chosen as some value. I don't know what the value is. Okay, so sigma s and sigma t. So for each image, filter along x and y with Gaussian filters, then filter along t with Gaussian filters, and compute ex, ey, and et, like the frame differencing. Like, how do you calculate the simplest derivation method for ex and ey? Let's subtract the next column, previous column with the current one, and etc. How about et? Subtract this pixel's value from the next frame's value, etc. And then for each pixel, okay, around this 5 by 5 neighborhood, compute this value, ATA inverse times ATB, if you can. Okay, if you can, then that means that you get your optic flow vector. If you cannot, then you will say that I can't do that. So your optic flow vectors on typical images will look like this. Okay, it will be vectors there. Can you see those? Maybe make it clear. So like this, maybe for these pixels, like that, and for the others maybe they will like this, getting smaller. For the rest of the image you will not get anything, because for the rest of the image there is an aperture problem. You can't find the motion because of the aperture problem. Maybe it is flat. Okay, usually if you have a let's say I have an object like this, and this one is rotating around this point. It just rotates around this point. Okay, what kind of optical vectors would I get? Maybe large one here and large one there, a little bit small one there, just a small one here, just a small one here, there, right? Maybe a small one here like this. You know that, right? Note that I only place some arrows around the edge points, because in the center of this object or in the background, my aperture problem will tell me that I cannot calculate the optic flow vector for those. Okay, only those parts will be visible. That's what the optic flow is going to do for you. Okay, good. So that's the differential technique to calculate the optic flow vectors. Again, why are we calculating the optic flow vectors? Because I need to estimate the motion field. I know that the motion field doesn't exactly correspond to optic flow, I know that, but it is better than doing nothing. That's the solution I find. Then you may ask, why are we trying to find the motion field vectors? Well, using the motion field vectors, remember, with the motion field vectors, I can do many things like the time to collision, or I can estimate the motion of the camera, also the depth of the objects from the motion field information. We are going to see one example right after this chapter. Again, remember what we said to calculate the optic flow. We have two methods. One is a differential technique that uses this technique. The other one is the matching techniques, like we did with the stereo feature matching. Okay, you calculate features from images. Okay, and then you match those features, and after the matching, you have the motion field vectors or optic flow vectors. Then you estimate your shape of the objects. Okay, so feature matching is something, I'm not going to do it, I'm just telling you how to do it. Let's look at one. Remember what we did before. We assume that given this image, we assume that this 5 by 5 patch goes through the same motion. Okay, so its vectors are same. They are like this. They all the same. So I can represent this patch with a simple V, just two numbers, right? Well, this is not a very realistic assumption, because especially if you think about rotation, rotate this patch around the center. In the center, my velocity will be 0, but when I get away from the center, my velocity will change. It will be different, and magnitude will change. So this is not a very good assumption. So some people said that, okay, when we are estimating the optic flow vectors for a patch, let's do this. Okay, let's do this. For the center pixel, let's assign a weight to it, and its weight should be higher to calculate when I'm calculating the velocity vector v, right? When I get away from the center, then the weight should change. That's what the suggestion is. Then we say that, well, we are lucky. We can modify our previous algorithm in a very simple way. Remember this algorithm that we said that the image gradient times v plus time gradient should be equal to 0. But I know that if the v is the common for the whole patch, it's not going to be exactly 0. It's going to be an error. Okay? So what I'm saying is that to calculate this stuff for each pixel, I know that when I do this, I should get ET value, but because of the error, I won't be able to get it. So to calculate this stuff, if I multiply this equation, multiply this equation with W1, for example, and this one times W1. W1 is just some kind of a weight. If for this pixel, if it is near the center, I am going to keep this W1 high. If this one is near the center, near the edge of the patch, then I am going to keep this W1 small. So what does that mean? For each pixel in my image, I am going to write like W11, W33, W55, okay, W15, and etc. Each pixel has a weight, and this one has a higher weight. Okay, so I am going to do this so that if I am making a mistake, I am going to bias this mistake towards the center pixel. Okay, so I am going to do this, and this is how I will do that. Okay, let W be a diagonal matrix with weights. Okay, and remember this equation, linear equation: A times V equals B. For a 5 by 5 window, this one was A times V equals B. This one is 2 by 2, right? How about this one? A is 25 by 2. B is what? 25 by no, it is 25 by 1, right? It is B, right? Just 1. Is that correct? No, it is not. Well, B is just a number. Yeah, it is 25, just 25 by 1. So it is, this is not 2 by 2, this is 2 by 1. Right? Okay. So, I have 25 pixels, and for each pixel I like to assign a weight. This is how you do it. Take a W matrix, and it's going to be a 25 by 25 matrix. Okay, and these are the diagonal values, and this one is the weight for the upper corner pixel, and this is the weight for the lower right pixel, and I have 25 numbers in here. Okay, the rest of them are going to be all zeros. Okay, rest of them are going to be all zeros. So this is a weight matrix. So if I multiply this weight matrix with the left side, if I multiply it with the right side, I am fine. Okay, so let's solve this one again. I know W, I know A, I know B, I don't know V. Okay, so the same thing again. So take the transpose of WA. Okay, remember, if you take the transpose of WA, it makes A times AT times WT, right? That's what it says. Okay, so since this is a diagonal matrix, taking the transpose of it doesn't change anything. So it would be AT times W, AT times W times A, the same thing here, and then so this is W times W, this is W square, and then take the inverse of it and multiply both sides, and this will be your new equation, V. Your new V is this, AT W square A minus 1T. It looks complicated, but it is not actually. It's just same thing. If you can invert this, then this is solvable. If you cannot, then this is not solvable. And solving this is not a very big problem. So optic flow works exactly like that. Okay.
Can we use SVD if it is not invertible? So invert it, like.
You mean the pseudo inverse?
Yes.
Yeah. You mean the instead of minus 1, you mean plus 1?
Yes.
Well, you could, but you cannot trust your. You cannot. But that would be your best guess. Okay. If the exact inverse is not available, then they are using the pseudo inverse, and there is a mathematical justification for it. But that doesn't mean that you are estimating your V's correctly, because you don't have the information. I mean, it does look like you are taking the perfectly white wall with your camera, and you are moving your camera around, and you are trying to estimate your optic flow vectors from the perfectly white wall image. And as a human being, when I look at that video, I don't see any movement, right? Nothing is moving, although the camera is moving. So optic flow doesn't correspond to motion field in that case. If you run your algorithm like that, so that will come back as you cannot invert it because your rank is 0. Okay. So if you get the +1 here, of course you are going to get some number, but that number is going to be some crazy number. Okay. So if I have the optic flow vectors, okay, if I have the optic flow vectors, it's like this. This is frame number 1, frame number 2, frame number 3, frame number 4, and frame number 5. And I get vectors, okay, like that. For each point, let's say, somehow I got these vectors for each point. Okay. These vectors are because my camera is moving, one thing. The other thing is that the scene is moving too. Okay. Let's assume the scene is not moving, but the camera is moving. My camera is moving. Looking at this is my camera, right? I am taking the video of this room by doing this, moving my camera around, and I solve this optic flow problem. Okay. I solved it. I have all the V vectors. What am I going to do with these? Okay, how am I going to solve the structure from motion problem? This is usually what you would do. Let's say if the scene is not moving. If this is my object A, object B, and object C. Okay, and if my original camera is at this position, my next camera position is here, and the other one is here. Okay, so this one will look like here, here, and there. This one will look like here. This one will be here maybe, and for that one it's going to be here. For the red one it's going to be here, then this one here, and this one is there. So I have 3 images or n images. Each one is looking at the same scene, right? The camera is moving. When the camera moves, what do? Okay, I know that my intrinsic parameters are not changing. Okay, my intrinsic parameters are not changing. What is changing? For this one, remember K times RT. Okay, this is R1 T1, K R2 T2, and K R3 T3. So 3 things, okay, 3 matrices. Their K intrinsic parameters are the common thing, and I know the correspondence between these 2 and these 2 because I have calculated the optic flow vectors. So I can say that I don't know these positions, this P position, P1 position, P2 position, and P3 position. So 3 unknowns, and 3 unknowns. For this rotation matrix, I have 9 unknowns, 9 and 9. Translation vectors 3, 3, and 3. So total of 9 unknowns here. 9 for the 3 is 18, and 27. 18 plus 27 is like 45 unknowns. Okay, 45 unknowns. How many knowns are there? I know that this P1 corresponds to this one. So I have a equation set. P1 times all these equal to this one. P3 times all these equals to this one. I have many knowns and I have many unknowns. Well, unfortunately, I cannot write one large linear system to solve for both R1, T1, R2, T2, and P1, P2, P3. Instead, I have numerical approximators. I can say that, okay, when I multiply this P1 or P3, okay, with K R2 T2, I will get this number here, xi1, yi1. Okay, so I know x's, I know k's, I don't know this one and this one and this one. Let's assume that my P's and T's are this. Start from a initial guess. Okay. If you put your guess numbers in here, if you are not getting very close by results, then you can change your RT and P values slightly and run this again. RT and P numbers slightly and run this again. And if you do this in a smart way, there is a way to do it. You are going to get your final values for P and T and R. That's called structure from motion. And this thing that we are doing is iteratively, it is called bundle adjustment. Bundle adjustment. This bundle adjustment is very useful and it works really. You get all of your stuff and you try to, by iteratively running this, you get your R values, T values and P values. But the thing is that you should start from, if you assume your R, T and P, they are all 0, were starting positions at the beginning, that's not going to lead you anywhere. You should start from something meaningful, something good. And for that one, I am going to show you one example. Before I am going to show you that one, maybe I should give you, let me show you that one, structure from motion. There was open this again. There was I am not connected to internet. Maybe I should do it this way. No, okay, structure from motion. There was a nice example somewhere on the, okay, this. I am connected. YouTube stuff. Structure from motion pipeline. This is what you do. A little bit different from what I told you, but in essence it is the same thing. Okay, first take lots of images of the object. This is just a castle. You take many images with a moving camera around this shot, around this castle. Okay, and then instead of running our dense optical flow method, this guy is running this feature-based method. It detects lots of edges, corners from each of the images and tries to find the correspondence between them. To identify points in the images that can possibly be detected in the other images. So identify the points, those red dots, and search for correspondence using some kind of a Ramsey algorithm or the algorithms that we have talked about. So these are the correspondences between all those images. In a way, I am calculating the optic flow vectors. Okay. Then compute the camera positions and 3D point positions such that the corresponding weaving rays intersect, exactly like that. Okay. The picture that I am trying to show you. 3 points in the real world. Okay. I don't know their, let's say, these are the 3 points in the real world. Okay, or 3 points in the real world. I don't know their positions, X, Y, Z values, but I don't know their positions on those images, right? I know them because I found the correspondences. And the other thing is that I don't know the rotation and the translation components of this camera, R and T values. And then again, R and T for this one. I don't know those. But starting from some smart initial guesses, I can put all these values in those equations. If they are giving me almost correct results, then I say that, okay, this is good enough. Otherwise, I keep changing my values. Okay? So this one looks like, well, it is going through all of them, right? These are very good guesses. So I have 3 guesses for these points. Okay, what happened? Okay. Stop. Okay, maybe go a little bit. Yeah. So I have, how do I do? Okay. I have good guesses for these three. Okay, 1, 2, 3 points, 9 unknowns, plus the unknowns of all the cameras. If my guesses are right, then if I put the equations, if I put my guesses into the equations, they should project them correctly in these positions, right? This place, and that place. I don't know what's going, this stupid YouTube, yeah, okay. So that's what I'm doing, okay? Do it. This is called bundle adjustment. After the bundle adjustment, I recovered my camera positions, okay, R and T, plus the positions of the points. So this guy has found 675 three-dimensional points of this castle, okay. No. It used 675 images, and he has more than 50,000 3D points with the correspondences. So that's lots of calculation. And after that, they calculated they have calculated the XYZ positions of these 50,000 points, also the camera positions too. And then they visualize it. Okay, this is the visualization of the recovered points. Okay, since I know the XYZ points of each of them, I can, using computer graphics, I can look at the scene from any point that I like. Okay. How about those green rectangles? What are those green rectangles? What are those green rectangles? Yeah, they are the camera positions, exactly. Because structure from motion means you are recovering the structure of the scene plus the camera positions too. Okay, plus the camera positions too. Okay, so I can, as I said, I can change my virtual camera anywhere, and I look at those point clouds that I have recovered. The nice thing is that I know the surface texture actually. Put the surface texture on it, and you can get this kind of a. Some parts are empty because for those areas I don't have the correspondences, because I don't have the image information maybe, or maybe my feature detector didn't work very well. Okay, it is exactly the same virtual camera motion, and that will be it. Okay, so non-sequential structure from motion. This guy, I guess, just ignore the time part, or they thought that it's just a one large stereo setup kind of thing, right? So that's the main idea of the structure from motion, and that's what we get. But the thing is that how do we get these initial R, T, and P values? Because these numerical methods, they don't easily converge to the final results. You need to start from a very good case. For example, if this is my function, okay, if I am going to find this minimum point, maybe somebody told me that, okay, this is your function. They gave me this function fx, okay, and they asked me to find the minimum of this function. I can test it, but testing it from minus infinity to plus infinity is going to take lots of time. And I'm going to do this gradient descent. Start from a random position like this. Okay. If I move this way, I know that it's going to drop. I lead it a little bit, and at here, I cannot move to the left or to the right. So I say that I found local minima. Is this the global minima, optimal value? I don't know, it's just a local minima. But if I am lucky, I started from this position, and it can go down and down, and I find it. Again, I am not sure about this, but this is the global minima. What I'm saying is that if you are lucky, or if you are smart, you would somehow start a position like this instead of a position like that. Okay? A position like that. You might, for example, if you started from this point, although this point is a smaller value than that one, you will end up here, right? And you won't be able to recover. Okay? But starting from this position is better. What I am saying is that if somebody helps you, say that start from this position, you are going to find your final results much better, then we should use that one. And I am going to give you an algorithm to do that one. Good? Any questions? Bundle adjustment is built in on OpenCV, and structure from motion is available from OpenCV. You can give your sequences, and it will give you your positions back. By the way, I mean this one, not this one, but this one. Okay. When it produced these point clouds, it doesn't know the exact XYZ positions in the real world. Okay? Say that, okay, assume my 0, 0, 0 is here. Okay? It doesn't know the exact positions of it, and it doesn't know the exact measurement between these 2 points. Okay? It doesn't know the exact measurement between those 2 points. Okay, it says that if the difference between these 2 points, the distance between these 2 points is 1 meters, then the distance between these two is 2 meters. It just can relate to each other. So there is one common scale factor in these calculations. That's easy to find maybe by making some. If I know the measurements of the windows, for example, the width of the windows, height of the windows, maybe I can recover that scale factor, or maybe some other value. But most of the time, I don't care. The important thing is that this relative recovery of these images. Okay, so let me stop at this point. Let's take some break. After the break, I am going to show you structure from a simple structure from motion algorithm, and that will have lots of assumptions, but at least it's going to give us some initial estimates for the point positions and the camera parameters. Okay, 15 minutes. Let's be here around 15:45. Efendim? Hayır.
Bunu şeyi göndereceğim.
Evet, sen de doldur. Şeyi doldurmuşsun.
Yani 20 gün için ben şey diyeceğim, siz 20 güne bunu fixleyin diyeceğim. Yani ben bu arada çalışmam için fixleyin diyeceğim. Başka bir yük doldurmam gerektiğince.
Abi şu ben burayı doldurdum. Bu çıktığını istediğim gibi doldurmadım.
Tamam.
Bak söylediğini doldurdum. Çocuklarını doldurmadım. Hatta bunu buraya bir doldurmadım.
Yani onların...
Bizim üstüne izinlerini falan verdim.
Ha. Tamam, ben onu silerim abi. Doğru diyorsun. Bunları gene ben yalandan yazdım abi. Onu güzel. Tamam, bunu göndereceğim. Diğerini de kendim dolduracağım.
Bir şey de göndereceğim. Üstad.
Ha, bakalım üstad değil. Bence yok.
Bir açsana. 78 program oldu.
Ha.
Bunun yanında değil. 75. Şu 77.
İşsizlik kapısı var.
Tamam.
Ha. Güzel.
Türkçesi. Şimdi şu kısmı doldurdunuz ya. Şuna doldurun. Şuraya iletişim noktaları verdim.
Okuyun kızım.
Abi ders çok iyi.
Abi ben bilmiyorum. İlk albüm bir şey almışım. Bu ders çok iyi gidiyor.
26'ın telefonu falan yazdım.
Şey,
Aynen.
ilk sağlasam ben
Fax mı? Fax yapıyordum.
262 yazıyor da yani.
Şimdi sola. Sadık mı?
Ya ama bu çok konulara hazırlıyorum. Ellerim.
Abi diğeri bir de şey.
Excel çok iyi abi Excel ya.
Zaten
Abi bu son ders mi? Hoca hiçbir şey dedi mi? Telafi falan yapacağız diye.
bir şey. Yani.
Ben çok duygulandım abi ya. Bu arada bir aklıma geliyor sen de düşünün sonra. Paramparça oldum ya. GS'yle bir daha ders yapamayacak mı abi?
Sen daha neredesin?
Abi ama gene de yani gitti yani olmadığını fazla. Lisede hiçbir şey önümde olmadığı için bu kadar kurulmamıştım.
Hafif bir hüzün olabilir. Normaldir.
İstediğin farkında mısın?
Ondan borç yok. Fena hızlı dolduramıyor ya. Nokta da takmıyor yani.
17-8'leri falan.
Neyse bir olmuşlar ama. Abi 17.06'da 28. Niye o kadar çok yaptın?
Bilmiyorum ki abi fixlerden işte. Arada kurban bayramı falan var, çok fazla gün gidiyor. 23 günün olması lazım. Sadece hesaplı söylüyorum ama işte öyle biliyoruz. Bunlar da herhalde aynı oluyor abi.
Ben 20-25 yaptım. 20 yaptım. Yılmaz hocam. 25 demiş. Öyle dediler şimdi.
Ha iyi.
Onlar yazdım mı hocam?
Mesela
Onlar yazsın diye olarak böyle.
bunları da sanırım artık yani. Tamam. Oldu. Bununla öbürünü göndereceğim. Diyeceğim ki
Doldurun.
fixleyin kafanıza göre. Tamam abi güzel. Abi next. Bu toplantı var mı? Güzel bir şey. Biraz şey anlattılar, teknik. Süreçler nasıl işliyor hocam? Abi güzel, son aktif falan kullanıyormuş CSE olarak. Ben çok data science, CSE'de GitHub bunları efektif kullanan çok şey bilmiyorum yani bilmiyorum. Yani bir sevindim yani. Tamam dedim en azından.
Ne
Doğru
kullanıyormuş
yani.
abi bu da çalışmıyor.
Sonar küp kullanıyorlarmış abi. İşte CSE'de tutuluyormuş abi kodların şeye uygun mu? Web 8 var ya Python'da. Web 8 uygun mu?
Anladım.
Genelde başka rule tanımladılar sonra uygun mu? Kod atarken önce ondan geçiyormuş sonra
Evet.
öyle bir görüşüyormuş.
Evet.
Olması lazım tabii ki böyle şeyler
Evet.
ama olmuyor genelde abi. Yani data science'lar falan, developer'da zaten şart oldu.
Evet.
Data science isteyebilirler hani GitHub'a sadece basıyoruz.
Abi sen çalışırken şey yapıyor musun? Git gibi bir şey kullanıyor musun?
Yani eksimde kullanıyordum. Zorunlu değildi. Koçta daha başlamadım artık çalışmaya.
Ha
Ama
mesela
kullanacakmışız.
notebook'ta
Gitmiş.
falan çalışıyor da genelde.
Hı hı.
Orada iş yapıyor mu?
Git mi?
Ha.
Yapıyor abi. Niye yapmasın anlamadım.
Nasıl süre falan bilmiyorum arkada. O ipeğine bir uzantılı montajlı.
Abi o da bir fark. Ha, sen onu nasıl dönüştürüyorsun? Çok
İpe
güzel.
gitti görüyorum yani.
Ben atıyorum, hiç düşünmedim abi, çalıştım. Nasıl yapıyorlar bilmiyorum.
Her şeye baktığında böyle güzel bir şey biliyor musun? Konu psikolojisine bakınca. Nereleri değiştirmişsin, hangisi halde değiştirmişsin.
Ha, yok abi, hiç bakmadım. Kendi iş soruyorum. Bakılır ama. Ben çünkü ödevleri de evde tutuyorum.
Bir de şey var, bana bilmem. Kolekte yazıyorum ya. Kolekte kendi psikolojisi var.
Ha, bakıyorum.
Girebiliyorsun.
Güzel abi. Abi böyle büyük mü mesela? Fazla olmuyor mu abi?
Yürür mü?
Olur.
Ben koridorda bu kadar ağır atlatmıyorum. Bir de ilk dönemleri varmış.
O tek bir ciddi mi?
Yok abi, şu.
Ha. Abi ben o tek oturuşta bitiriyorum.
Yani tek oturuşta
Nasıl bir ciğerim var abi?
bilmiyorum.
Allah
İşte
Allah.
20-20'şer dakikadan sonra 10-15 tane sonra. 2 yıl bir şey.
Yani bayrakta şey okuma, çizgi roman okuma gibi.
Resmimizi.
Var mı? Manga falan okudum da abi. Biraz şey ya, biraz daha batıya kapalı. Ondan da atmış. İyi iğneli gözlermiş abi. İyi olup da ben çok renk falan hatırlamıyorum. Sonradan bir tane biliyorsun. Çünkü şey abi hem sanat olarak bir maliyeti var. Adam hikaye anlatmak istiyor. Yani çizim yapmak istiyor. Ondan sonra boyayacaksın da dediğin zaman haftada çok hızlı dönmüyor.
Evet abi.
O yüzden siyah yazılar çok tercih ediyorum.
Bir de taşma yapmıyor.
Ha evet var var ama ben şeyden dijital olduğum için yok abi.
Burada ipap desteği kaç tane sınırlı var.
Orada da var ipap şeyde. Ha sen değil mi?
Burada ipap'ta kendi şey vardı. Ama bir de konusu vardı.
Dönmüyor mu?
Dönüyor. Ama bölüme gerek olmadı.
Ha tamam.
Destekleyecekmiş galiba.
Bir saçma bir şey var ya.
Şu baskı da bozuk şey oluyor ya. Bilmiyorum. Benimkini de bilmiyorum çevirdiğim için yoksa normalde olmadı. Bozuk oluyor. Mesela sayfa numarası falan da geliyor.
Ha onlar doğru gelmiyor.
Yani mesela şey noktasında sayfa numarası oluyor falan.
Anladım.
Ya da çok boşluk oluyor.
İşte muhtemelen dediğim gibi.
Çevirmeden mi oluyor?
Ya İPUB'da çünkü yok ama sayfa numarası normalde. Veya İPUB'u taratıp PDF'i taratıp elde etmişler. Sayfa numarası da yazıyor İPUB'da. Şey okumak, PDF okumak çok zor zaten. Kindle okumadan. Tatsız. Çok tat kaçırıyor abi. Hiç zoom yapmadan ne okuyacaksın? Highlight da edemiyorsun. PDF.
Size zor geçiyor sayfa işte.
Öyle bir şey o. Yani yavaş oluyor ya herhangi bir işlem. Orada işlemcinin küçüklüğü gözümün önünde beliriyor bir an böyle küçücük bir işlemci. Bütün veriler atıyor işte. Açık durmuyor.
Var ya benim mesela.
Bence de var. Ama hangi çağda nasıl hala şey olabilir? People yazıyor. Abi topla gitsin mi ya? Kalecilik öyle herkesin elinde akıllı telefon. Abi işte toplum çok daha yavaş ilerletiyor demişler. Sosyoloji. Ona bakmış. Geçeceğiz kişi ya. Sonra teknoloji. 1600'lerde nasıl yaşıyorsanız bilmiyorsun.
Yaşar bombalı.
Aynen öyle. Abi çok anlattım. Çok anlattım. Tutarlılığı da yok işte. Normalde adam gece yani. Deli gömleği giyiyor adam. Şey tımarhane yapıyor. Yani öyle bir adamın yazdığı bir şey okuyorsun. Yani tutarlı aslında. Bunun gerçekten bir fikir bakışı. Bilmiyorum. Çıkabildiğin insan gördüm. Zaten çıkarılır mı abi?
Yok.
Sen penaltı olursun.
Görmüyorum.
Biliyorum.
Okay, so let's look at this structure from motion. There is a very well-known common algorithm, classical algorithm. It doesn't solve the whole problem of structure from motion, but as I said before, it's going to give us very good initial results. Okay, so that's the definition of structure from motion. Given a set of flow fields, that is the optic flow, either from differential technique or from the feature-based technique. Okay, we like to determine the sequence of camera poses. Camera pose means that for each camera, I need to get the RI and TI values for I frames. Also the structure of the scene. If we have n points that we are going to track or find, okay, we are going to find the three-dimensional positions of these n points. Okay, so I have this camera moving around my scene, and I am going to both find the camera positions plus the camera, the structure of the scene. That's what we are going to do. So this is called structure from motion. So structure from motion is something very useful, and these are the steps of it. Track a set of feature points through a movie sequence. Either you do this by optic flow or the feature-based methods, and then deduce where the cameras are, okay, the camera poses and the 3D locations. And after that, you do whatever you want with these 3D positions and the camera positions. Usually, we render synthetic objects with respect to the 3D geometry, and I have shown you the one example. Okay, so the algorithm that we are going to look at is factorization, 1992 paper. These are Tomasi and Kanadi, are very famous computer scientists, computer vision people. Okay, Carnegie Medal stuff. Again, we will come up with this SVD. We are going to use SVD to do the factorization, but to come to that, we will have to do lots of assumptions and some simplifications, and you might say that, well, this is too much, this is not realistic, and etc. But remember, we are trying to find some initial estimate for our camera positions, also the scene positions. That's what we are going to do. So you remember this. We are going to work in our camera coordinate system. So, yes.
Tesla has something like this flow motion in screen in front of the driver.
Yeah. Well, Tesla doesn't use any range radar-based stuff. They estimate their depth values from the image motion. Yes, I mean, if they can estimate the depth, they are estimated it from the either stereo, because I think it has 11 cameras or something, and also it has the motion information too. Okay, so I mean, you weren't here. I mean, in the previous lecture, I showed the guys how to estimate those positions. So if you are on an autonomous vehicle, and if you have a camera, it is moving around the scene using the structure from motion, like I showed you before. Okay, you can estimate the depth of the objects. So let's go back again. We are going to work in the camera coordinate system. If this is our world point, remember, do this, multiply it with this matrix, so this will take care of the translation. So I have tx, ty, tz, this one says that cx, cy, cz, and then I multiply it with the rotation matrix, and I get the projection plus. Okay, so this is both the translation vector plus rotation vector. I am now in the camera coordinate system. This is not image coordinate system, but the camera coordinate system. Okay, then if I multiply this PC with intrinsic, you would get P image, right? So that's it. But for now, we are in the camera coordinate system. Okay, this is something that we need to keep in mind now. Later I can generalize it to image coordinate system. We already know this. I think this is the maybe 15th time I am showing you the same picture. If you have x, y, z of this P, to get x and y values on the image plane, I use these simple formulas. But these are not linear equations. These are nonlinear, since I am dividing it by z. Since these are nonlinear, to build a linear system, I have problems with it. But this is the perspective projection. So instead of perspective projection, I can do this, weak perspective. Do you guys remember what weak perspective is? You assume that all of your objects are z0 away from you. Okay? So they have their own xyz values, but they are away, they are constant distance away from the camera. So the camera is not that close to the object itself. It's like an airplane. Okay, the airplane is taking the pictures of the surface of the Earth, because the airplane is maybe 500 meters from the Earth's surface. I can assume that all of my objects are around 500 meters away from me. So instead of dividing them by the z, which depends on where the object is, I am dividing by this z0, which is a constant, which makes it all linear, right? So multiply x by this number, f over f0, z0. Okay, so this is called weak perspective projection. Okay, so again, assumption, but it's going to make our life a lot easier. Okay, it's going to make our life a lot easier. You might say that if my camera is not that far away from the real world objects, that's going to give me a problem. Yeah, that's true, but remember the picture that I showed you? This one? There is a reason why they have taken the images of this castle. Why? Because to take the image of a castle, you have to away from it, right? It's like always 30 meters away from this castle, right? 50 meters, 30 meters. So there is this. So for this image sequence, this assumption kind of holds. Okay, this assumption kind of holds. So instead of using this formula, I am going to use this formula. Or in fact, why don't I just take this division f over z0, okay, used as a constant number. So it's like orthographic projection. Just ignore this number, right? Okay, just take it like 1. Okay, so it's going to make our job a lot easier. So our projection became x is equal to x, y is equal to y, and ignore z. Okay, that's it. You might say that, well, I mean, this will not make any difference between a very large object and very small object, and that's right. I mean, I don't know, by looking at this picture actually, I don't know if this is a toy castle or the real castle. Okay, I don't know, but I don't care. The important thing here is that what is the relative distance between the scene points and the relative distance between the camera and the scene points. Later I can always multiply those distances with a constant number, which is this f over z0. Okay, so pure parallel projection, highly simplified case where we ignore even the scaling due to distance. Okay, so this was the original projection stuff, remember, from the camera coordinate system to the image coordinate system. F and 1 is doing the projection. Okay, and in the homogeneous coordinate system, x prime over z prime is this. But with our new assumption, it dropped down to this. So what happened? So 1 times x times z, 1 times x times 0 times y, 0 times z, 0 times 1. So it is like x prime is equal to x, y prime is equal to y, and that's it. So our system is just pure linear and very simplified. Very simplified. Okay, that's my assumption is. Okay, let's put this is my intrinsic matrix now. See, this is my intrinsic matrix. I ignored F and Z. Intrinsic matrix. This is my extrinsic matrices, rotation and translation. Since I have ones here and 0 there, let's see. This 0, right, is always multiplied with this row. So this row doesn't have any effect, right? And this 0 is multiplied with this row and it doesn't have an effect. Okay? Sorry, I didn't mean that. Okay, this 0. So maybe use a different color. So this 0 is multiplied with this. So these two rows of those matrices are gone. So that means what? I don't have to calculate the third row of the rotation matrix. Because with this assumption, third row of the rotation matrix doesn't make any difference for me. You might say that, well, how are you going to recover the third row of the rotation matrix? Well, remember what was the most important feature of the rotation matrices? Rotation matrices are what? We have used this property many times. Rotation matrices are what? Orthogonal. Right? What does that mean? It means what? If I multiply this row with this row, it should give me a 0. Dot product, right? Also, if I do the cross product between these two, right, it should give me the third row, right? So that's the meaning of it. So what I'm saying is that if you can guess these two rows, the third row is automatically found. Okay, so that's good. That's good. So instead of looking at this picture, let's look at this picture. Okay, let's look at it is more simplified now. See, when I look at this linear system, I don't know the real world coordinates of the points x, y, z, the same point. I don't know the camera translation vector. I don't know the rotation road vectors of the rotation matrix. All I know is this x, y, because on my image I know them. Well, I mean, if you are looking at a single image, there is no hope of recovering 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, 10, 15 unknowns just by looking at just x, y value. Right? But the thing is that I am going to take many images of the same scene with a different camera coordinate system, right? Camera system. The same camera is moving around, and I know that they will correspond to each other. So I know that the point did not move, and I know that these values change, and I know these values change. I know the corresponding x, y for each image. I know those. Okay. So basically, this is gone. This is gone. Similarly, because of these zeros, okay, this is gone too. So I end up with this small system. How many unknowns? 6 here and 6 here. Total of 12. Total of 12 unknowns per given a point, okay, and a camera. So RC here, okay. But on a given image, I have many points. So from each point, I will have 3 unknowns more, but the camera parameters will stay the same for a given image only. Okay, so let's write these equations in a more compact way. If I take the Cx from these p values and multiply it with this it, okay? That's the first row of the rotation matrix. So it times p minus t is equal to x, jt times p minus t equals to y. Again, it is the first row of the rotation matrix, jt is the second row of the rotation matrix. Okay, good. So for a given image, I and t is fixed. Of course, p is changed. For each p, there is an x. For each p, there is a y. Okay? So good. Okay. So at the beginning we have this. Okay, we have this. I have this equation set. I have n points. What was the number of n in the video that I showed you? 50,000. There are 50,000 points that I am tracking, and there are f frames. How many frames did we have in that video? 6,000, right? Yeah, so f in our case is 6,000 and n is in our case 50,000. Usually n is much greater than f. And this f is a very big f. I mean, 6,000 f means that if I take 30 frames per second, that means what? Divided by 30, so it means 200, okay, 200 seconds of video. Well, I mean, that guy had much longer than that. Maybe he took 10 minutes of video and he selected some of the frames very carefully. Okay? So, I have this equation set, okay? Let's look at this one. Xij means that I is the okay, let's look at this one. I is the frame number, j is the point number, okay? Xij means that x position of the ith frame of the jth point, and yij is this. So how many xy's, how many xy pairs are there? How many xy points are there? Pairs are there? One of the x's is here, the other one is, one of the y's is there. How many xy pairs?
50,000 multiply 6,000.
Yeah, n times f. So I have n times f number of xy pairs. Okay? Because for each image, I have n points, and for each image I have the projections of those images, and I have f images, right? Okay? So I have n 50,000 points, and I am getting those 50,000 points for each image. Okay? Good. So from 1 to n points, and these are my rotations. Okay? First row of rotation, second row of rotation, and these are my translation vectors. So this has 3 unknowns in it, 3 and 3. Okay? For each frame, I have 9 camera related unknowns, and for each frame I have n times 3 scene related unknowns. Okay? So there are total of 9 times f times n times 3 unknowns, right? Very, so f times n is what? 50,000 and 300 million. We are talking about 1 billion unknowns, right? So we should come up with a linear system that should give as a solution 1 billion unknown. Okay, so the very large linear system. And without building a linear system, actually, you cannot come up with those kind of stuff. Okay, so I think you might have noticed that linear algebra is a very useful thing. Without a linear algebra, nobody can talk about finding 1 billion unknowns with a very simple algorithm. Okay, so we know these. Okay, so 1 billion, almost 1 billion x and 1 billion y's. We like to recover these. We like to recover these, and we like to recover i's and t's. So let's use some tricks. What did we say? Well, I am living in the real world coordinate system, but I don't know where the 0, 0 is. I don't know the difference between 2 points. So why don't I use a very convenient real world coordinate system? This is what I'm going to do. I am going to set the origin of the world coordinate system to the center of mass of the endpoints. I will take these endpoints from 1 to n, add them up, and divide them by n, and I will call that point 0, 0, 0. Okay? Whatever my points are, I don't care what they are, I will assume that their center of mass is going to be 0, 0, 0, 0. Okay? 0, 0, 0. So, what do I do now? This is a very special point now, the central points. Whatever the points are, okay? Whatever the points are, I will move them in a way that their center of gravity, say the center of mass, becomes 0. Okay, then maybe I can talk about this. Remember this one? IT times PJ TI. This is how I will get it. Okay, if I add all the points, what did I say? This is going to be 0. Okay, now I am adding all the points, the projections of those points. This is the projection of those points. Okay, add them up, divided by n. Let's say this is xti. So what does that mean? It means that give me an image. Okay, give me an image number t. Okay, on this image I have n points, xy points. Okay, if you add them up, if you take the average of all of those xy points, or the center of mass of xy points, it's going to be this value. Okay, so x bar ti, it means that x bar ti means that for the frame number t, if I take all the points, add them up, take the average, you are going to get this value. So it's going to be, for example, this point. Okay? So for each image I can calculate this, right? Because for each image I know my 50,000 points. I can add them and find this value in there. And if you do this, multiply this one and multiply this one, what do I get? 1 over n times from I1 to n ITPI minus 1 over n ITTT. Okay? I know that this one is 0. How do I know that? Because I assumed it so. Right? Why? Because, well, you might say that there is an IT in here, but I can take the IT out, right? Take the IT out, and all those additions are going to make me 0. How about this one? This one is something different. This one is something different. What is it? It says that I is from 0 to, what is this? This is I, right? I is changing from 1 to n. Well, I don't see any i's in there, right? So I keep adding this n times and dividing it by n. So this will cancel out. So it's going to be ITTT. Very interesting, right? So what does it say? It says that the center of mass of all these 2D points is now became IT times TT. Remember, IT is the first column, first row of the rotation matrix, and TT is the translation vector. If you multiply these two, dot product, it should give you minus ITTT. And that's going to give you the X component of your center of mass. Okay? That's a very valuable information. Why? Because I can calculate this red dot from my observations from my image points, right? I know this part. I don't know these two, but I know this one. So I get the multiplication of these two vectors. That's very good. And if I do the same thing for the y part, I will get another equation. Okay? So that's a very useful thing. We are going to use it. Okay? With the factorization approach, I have this one, and therefore the y. From this one, okay, and I do the same thing with the y. I get this, and I get this. That was the first trick. The first trick came from this one. I set the origin of the world coordinate system to be the center of mass of the endpoints. Okay. The second trick now, we are going to do this. Subtract off the center of mass of the 2D points in each frame. So remember, this is the center of mass of the each image point for each image. Okay. If I subtract this value from each xi, okay, I will get this one. And in fact, I can calculate this one too. So if I take this value from each xi, I know this one, it is this. And I know this one too, it is this multiplication. Okay. And this one is IITI is going to be this. Okay. So they will cancel it out. It's going to be like this. Okay. They will cancel it out, and I will end up with this equation. So what does it say? It says that for each point on your image plane, okay, if you subtract this value from your point from the image plane, you will get this value. This is very, again, this is as useful as this one, because now we are talking about for each point now. Okay, for each point, of course, I can for a given image, get all the points. Okay, calculate the center of mass. This is my center of mass. Okay, subtract the center of mass from each point. Okay, that value will give you this IT times PI. Previously, I had this ITTT. So it is talking about the same frame. Now we are talking about okay, ITPI. Okay, one is about the image frame, the other one is the point itself. Okay, so now we started talking about the points. Previously I was talking about the frames only. Now we are talking about the points too. Okay, so far we removed the unknown camera location from the equations. More importantly, we can now write everything as a big matrix notation. So this is our big matrix. This is a matrix of size 2f, and what is 2fn? How many? First of all, for each point, okay, this is my first row, point 1, point 2, point 3, and point n. So there are how many points, how many columns in this matrix? There are This part of the matrix is the same size as this part. Okay? The upper part is f by n, the lower part is f by n. Since I have two components x and y, so this is f by n and this is f by n. If I put them together, it is 2f by n. Okay? So that means what? That means I have n columns and 2f rows. Okay? All n points in one frame. So, good. The interesting thing is, for each x11, x12, these are the what? Why are there tildes? These are not my original. These are not my original image locations. These are the image locations with this one. From each one, I subtracted the center of mass of that image. Okay, so these are modified image locations. So I get all these values, put this in a matrix, but I know that each one is a multiplication of these two values, right? ITPI, GTPI. Okay? And because of this subtraction, okay, these TI went away. I don't have the TIs. I don't have the translation vectors in this case, okay, because of the trick that we use, our second trick. They are gone. All I have is the rotation vectors, or the rows, rotation matrix rows. Okay, so each one is a multiplication, so I know this one. Okay, so why don't we write this one as a multiplication of these two simple matrices? Remember, x tilde 1 1 is equal to I1t times P1. X tilde 1 2, okay, is I2t times P1. Okay, so multiply this with this, write it here. Okay, and multiply this with this and write it here. Just a simple matrix multiplication. This is 3 rows by n columns, and this is 2f rows by 3 columns. Why? Because for I and j, I have 2 components of R, right? Okay? This part, I know all of them, okay? I know all of them, 2f by n. I know all these points. This part only comes from the images. This part is the unknowns, okay? If we look at it carefully, this part is just about the seen points, right? This is structure. This one talks about P1 to Pn. This is just structure. This part is about motion, right? This is motion, this is structure. That's why we call it M and we call it S. This is a very large square triangular matrix, okay? 2f by n, very large one. This is a narrow but long matrix. This is a very wide but short matrix, right? Okay, so I don't know any of these. I don't know any of these. So if somehow, if I can factor this matrix into this kind of matrix shape, matrix multiplication, then I recovered everything. That's why this approach is called factorization. Now I'm going to show you some linear algebra stuff again. See, whenever we do a linear algebra, what do? What did I say about whenever you are doing something linear algebra, either equation solving or some other stuff?
The inverse of the matrix.
Well, I mean, I cannot take the inverse of it. Even if you are doing the inverse of the matrix, what do? I always start by doing what?
I remember something about eigenvalue, maybe it's about
I don't understand what you are saying.
eigenvalues.
Even if you are doing the eigenvalues, you start doing what? Singular value. Well, I mean, you should know this by now. Singular value decomposition. Okay? We are going to do the singular value decomposition again, but how? Why? Let's look at this one. The linear algebra theory says that, okay, linear algebra theory says that, okay, of course, if you multiply this one with this one, you are going to get this. I have this matrix, but then I have these, okay? I don't have those. I am trying to get those, okay? This is how I'm going to do it. Okay, factorization approach. Rank theorem says that, okay, rank theorem says that this matrix can have at most a rank of 3. Okay, a rank of 3. It's a very large matrix, but it is all empty, it is all redundant. Okay, why? Because if you have such a multiplication, okay, rank of an m by n matrix is at most minimum of m by n. So if you have a 100 by 3 matrix, rank theorem says that this matrix can have at most a rank of 3, minimum of it. Okay, doesn't matter if this is 1 million, your rank cannot be larger than the minimum of your dimensions. That's one thing. If you are multiplying two such things, okay, what is the rank of this matrix? It is at most 3. What is the rank of this S? It is at most 3. If you are multiplying two matrices with a rank of 3, okay, the rank of this W cannot be larger than 3. Okay, so that's why we say that the rank of this matrix is just 3. It could be at most 3. So why is the good thing to know? Because we are going to do the singular value decomposition. We are going to say U D V transpose. Okay. Since we know that this is a rank of 3, this will have many diagonal elements, but we are going to say that your only 3 diagonal elements will be non-zero. The rest of them will be zeros. If the rest of them are zeros, then I can ignore many parts of this U and many parts of this V. Okay? And that's going to give us a very nice factorization mechanism. Okay, let's look at it. Okay? So what is the rank of a matrix anyway? The rank of a matrix is the number of linearly independent rows or columns. Okay? Number of linearly independent rows or columns. What is linearly independent row or column? Can anybody tell me?
We can make another with coefficient.
Exactly. If I have this many rows, okay, if I can represent these two rows with a combination of linear combination of other rows, then that means that they are linearly dependent. Okay, so let's say, okay, I have two numbers. I have these numbers 2, 3, 4, 5. Okay, I multiplied these numbers by 2, 8 and 10. I multiplied these numbers by 3, it's going to be 6, 9, 12 and 15. These are linearly dependent. Why? Because I obtained these numbers by multiplying with the same constant, right? So the rank of this matrix is just 1. I know that one, because I produced it. So if somebody gives you 2x plus 5y equal to 6, just one equation, two unknowns, you are not smart by saying that, okay, I have 2, 5, okay, one matrix, x equal to 6, then I would multiply it by like 4, 10 and 12. Let's solve it. You're not going to solve this because you didn't add any new information to this matrix. So because the number of linearly independent rows is just 1, not 2. Without the full matrix square here, you are not going to solve it. Okay? So the rank of the matrix, okay, when you are talking about just two-dimensional, three-dimensional matrices, these are easy to see. But here we are talking about 50,000 by 6,000 matrices, right? I mean, without using these kind of tools, SVD kind of tools, you are not going to solve your things that very easily. Okay? So, what is the rank of a matrix? Number of columns or rows that are linearly independent. If a matrix is A is treated as a linear map, okay? If this is a matrix, if I can transform this n-dimensional space into a single dimension like this, okay, this matrix would have a rank of 1. Okay? This matrix has a rank of 1. Interesting stuff, right? Interesting stuff. Very special matrix for this one. Very special matrix for this space. It knows that space very well because it can reduce this matrix, reduce the space like a one-dimensional line inside this n-dimensional space. Okay, so number of linearly independent rows or columns, we know that. And when we come to this, I know the rank of this one is it can be at most 3 because I don't have more than 3 rows here. I don't have more than 3 columns here. If I multiply them, I am not adding new information to this matrix, okay? So this matrix cannot have a rank more than 3, okay? So that's good. What am I going to do, okay? It shows that the video data is highly redundant. It's just 3. I mean, that means what? I can represent this W by linear combination of 3 rows or columns. Very interesting, right? I am talking about 60,000 lines, but I can represent all of them with just 3 lines. Okay, so it is a very redundant matrix, and using the SVD approach, we are going to see we can precisely quantify this redundancy, and that will give us this nice algorithm for the structure from motion. Again, W is equal to U times D times VT. So if I do this, D will be a diagonal matrix. Only the first 3 elements of this diagonal matrix will be non-zero. The rest of them will be 0. So if I do this, it's going to be like this, right? A square matrix 2f by 2f, very large. N by n is very large. Okay, this is 2f by n, but only this one, and this one will be non-zero. The rest of them will be, I will assume, they all will be 0. Okay. Well, these are non-zero. Why am I making them 0? Okay. These are non-zeros. That means what? Only the first 3 rows will get multiplied by these 3 numbers. The rest of them I can ignore. Okay? Only the first 3 columns will be multiplied by these 3 numbers. Okay? And the rest of them will be 0. Okay? Did I? No. I did it wrong, right? Because only these 3, yeah. The rest of them will be 0. And only these 3, rest of them will be 0. You see where it is going, right? Kind of a factorization. Remember, I am trying to obtain this one. Get 2 matrices. One of them is, okay, like this. The other one is this. 2f by 3, 3 by n. Get me a very long but narrow matrix. get me a wide and short matrix. And this one kind of is giving me this actually. Okay, you can decompose your matrix into this U, D, and V. U could be this, V could be this, but how about these three numbers? I can factor those into, okay, these all should be 0, and only this part, only this part, and only this part is relevant. I cannot take, I cannot say that this is my motion vectors and this is my structure vectors, okay? I cannot say that because there is this 3 by 3 matrix in front. Okay, some smart people said that, why don't I take the square root of this D, multiply U prime with D prime, U prime with the square root of D prime, and square root of D prime and V prime, okay? So you get your 3F by 3 and 3 by N matrix. This is your motion matrix. This is your scene matrix. They said that, but if you remember, okay, this looks nice. If you remember, what did we say about the singular value decomposition? When you do the singular value decomposition, I know the rows, the columns, and the columns of these two matrices are orthogonal to each other, okay? They are orthogonal matrices, but they are not unique. If you do your singular value decomposition with a different library, this will be satisfied, but U and V will not be unique, it will be different. Okay? So what does that mean? My points are going to move around? That cannot happen. So what are we going to do? Again, we will come back to our rotation matrix. Remember, what do I have in this M? We have our components of the rotation matrix, and rotation matrix is orthogonal, right? So if the rows of this matrix are my rotation matrix components, when I multiply two of them together, it should give me a 0 because orthogonal. And if I multiply it by itself, it should give me a 1. Okay? So find the MS combination, factorization, in a way that my rows of M satisfies this property. Okay? So what I'm going to do is I am going to multiply this M with a Q. I am going to multiply S with a Q minus 1, just the inverse of it. So at the end it's going to be the same MS. But I am trying to find a Q such that this MQ produces rotation matrices that are really orthogonal. Okay? So what is the size of this Q? What is the size of Q? Okay, this is 3F by 3, 2F by 3. So I am going to do M times Q, Q minus 1 times S. What is the size of Q? Tell me.
3 to F.
3 to what?
F.
No. This is by, if this is 3 to N, this would be, first of all, I am going to take the inverse of it, right? It has to be square, right? So this is to be 3 by 3 and 3 by 3. Okay? So this is 3 by 3 and 3 by 3. That means what? I need to find these nine unknowns. So 9 unknowns, that will give me this IT-JT pairs that will make them orthogonal. This is not a linear problem, I am sorry. This has to be found using a numerical approach, and we will have to find this numerical approach and use some numerical solutions library to get these unknowns so that your I's and J's are orthogonal to each other. Okay? If I multiply I with these Q's, you should get 1. J's and J's 1. I's and J's should produce you 0. Okay? So once I solve it, okay, again bundle adjustment, I get the results. This is the YouTube video that I showed you. and maybe I should end this part of the lecture by running this again. This one doesn't use the bundle adjustment. This one doesn't use the factorization. Again, many images, 6,000 images, and I will have 50,000 point correspondences between them. Okay. You might say it doesn't look like there are 50,000 points on this image, on each of them. Well, I mean, the algorithm that I showed you assumes that you keep tracking the same point with on all these images. I didn't talk about what happens if I do it, because I cannot see the behind of this tower, right? Behind of this tower is not visible, but for some other images it's going to be visible. So my algorithm is going to fail. For those kind of cases, there are solutions, but I didn't talk about them. Okay. So this algorithm can work even if you lose tracking of some of the points. Okay. After the point correspondences. Okay. So before running this, before assuming the camera positions and the points, run the factorization algorithm to get your initial points and to get your initial camera positions. That's not going to be perfect because remember we assume that everything is orthogonal. Remember we assume that we are away from the we are the same distance away from the objects themselves. That's not going to hold in the real world, but that will give you very nice initial starting positions for your numerical approaches. Okay, and after that you solve it. After your solution, you get your point clouds. Okay, any questions so far? I guess that will be okay. Let's take some break. Let's be here around, I took too much time, 16:55, and after that I will, why don't I continue and finish up the lecture? Should I do that?
All right.
I was going to let you go 17:20. Now I'm going to let you go 17:05, right? Let me continue 20 more minutes, okay? Okay. Factorization summary. Assumptions is my orthographic camera and non-coplanar points checking in. What is non-coplanar points? Coplanar points is this. If you get all of your points from the same, plane, like this one, let's say this is the same plane, then this algorithm is going to fail. Remember your S matrix, Ace matrix, if you get all of your points from the same plane, your S matrix will not have a rank of 3. It's going to have a rank of 1 or maybe 2. Okay? Because it's a 2-dimensional information, not 3-dimensional. So you need to get points from this plane, also points from other planes too. Okay? That's what it says. Okay? So non-coplanar points checking in F greater than 3 frames. Okay, and then after that, for each point you are going to do this. You are going to calculate the centered measurement. For each frame, you are going to calculate the shifted points. This is MXJ is the center of mass of frame I for the X and Y. So calculate this mxj and myj, get these values. Once you get these values, now you have your large matrix 3f by n matrix. Okay. Once you get this matrix, run the singular value decomposition. Okay. After you get the singular value decomposition u, d, and v, okay, you know what to do. You just erase after the third diagonal element of d, make everything 0, and ignore the large part of u and v too. Okay, so you are going to have an m of this value, s of this value, and then find this q such that it makes the rows of this m orthogonal to each other. Okay, find a numerical solution for this one. After that, you get your motion matrix and the structure matrix. Structure is very nice. It's all your p values, p, x, y, z. It's nice. Motion is just rotation matrices and the first two rows of rotation. For the third one, it is okay. How about our translation vectors? Where are our translation vectors? This solution did not give me the translation vectors, but I can go back. Now I know this P, I know I know X. Get this T after that, right? So I can get these T's afterwards. Again, this will not work very well because of our orthogonality assumptions, but you can run your bundle adjustment afterwards. That's our algorithm, and these are some results. I think this is just a picture of the results. By the way, this is where I have stolen these my slides, their slides. These are not my slides, their slides. I think this person has stolen these from somewhere else too, but you know how it works. Okay, so it looks like this works very well with this kind of structure. I mean, obviously it's not going to work if you try to make it work with a flat wall. Okay, if I don't have any features, it's not going to work. You need to have lots of features. You need to have lots of trackable features, right? Without the trackable features, it's not going to work. It works very nicely for the satellites, observation satellites. The satellite is 300 kilometers up, right? And it is scanning the world. It's doing motion, right? It's in a motion way. It's taking many images from different angles. If you run the structure from motion on those satellite images, and orthogonality holds very well, right? I am 300 kilometers up, and I assume that, I mean, the highest mountain in Turkey is 5,005 kilometers up from the sea level, right? So if I am up 300 kilometers, I can assume that they are the same depth. It works very well, so you can get the height of the geographical structures very nicely, and tracking is good because other than the sea, and I know that the depth of the sea is just 0, right? Other than the sea, all the places in the real world are very matchable. And actually, this is how those cruise. What is the difference between a cruise missile and ballistic missile? This is your Earth, right? This is your Earth. Okay. And these are the geographic features of the Earth. Okay. Ballistic missile is this. This is me. This is my enemy. This is me. Ballistic missile, you just let it go towards space, and it follows this trajectory and it goes there, right? That's why it's called ballistic. Usually, this is 100 kilometers. This is the reach of the atmosphere, right? So this is the trajectory. It just this is nice. Why it is nice? Because while you are following this trajectory, after this part, you don't spend any energy, okay? This is your kinetic energy. There is no air resistance. You go up to the peak, and you follow your natural trajectory, and you reach whatever you like to reach. And if you are tough enough, you can resist the atmospheric re-entry forces and etc. But this is bad. Why? Because I have a satellite here watching you. As soon as they see you launch the rocket, they can estimate, they will perfectly estimate this trajectory, okay, and they will send a anti-missile rocket, and they will kill you there. So what is the other solution? The other solution is cruise missile. You send a missile, a rocket, okay, it follows this path and it finds you, okay. Very difficult to detect. It can avoid the radar detection because it's a cruise missile. It knows where the target is and it knows where it is. But how does this cruise missile knows where it is? Okay. Well, you might say that I guided through the satellite, but satellites can be jammed. So what do? They have cameras. Okay. They have cameras. Where is mine? Okay. They have cameras. They look at the underlying earth structure. From the structure of the motion, okay, they find the height of the objects, okay, they take those height of the objects, the mountains and the other structures, it makes a match to its database, and it knows where it is, so it can guide itself through the valleys, and sometimes it goes high and sometimes it is low, and it is flying very, very fast, and when it recognizes where it is, it can go down and cause some damage. So that's the difference between the cruise missiles and the free trajectory ballistic missiles. Okay, this is 1940s, this is 1950s and 60s. Okay, this is a German invention, American invention. Okay, and this was working before the communication satellites and etc. Okay, so this is important. Structure from motion is important. Good. So I showed you how to make missiles, so you are free to use it for good purposes. So after this I am going to talk about still motion. I am going to talk about some background detection, background subtraction. I have stolen these slides from this person. Okay. I don't know where he got his slides, or she, I don't know. Old ones, but the thing is this. Okay. Let's say I have a security camera looking at my highway, my freeway or payway, whatever. Okay, I like to isolate the objects that are moving, because on an image like this, objects that are moving are important, because on a highway, objects moving means that they are cars, right? If I can isolate this car here, I can isolate this and I can isolate this. In my next frame, if I do this T0, if I do this T1, if I can isolate this van in 2 frames, and I know that the time difference between them is 0.03 seconds, and it was here, now it is here. The difference between these 2 pixels corresponds to 30 meters and on that road, and this is the time it takes to travel it. So I can measure their speed, right? So this is how the speed measuring cameras work. But before the speed measuring camera does its job, I need to extract this. Okay, so these are the stuff that are moving on this image. This is a car, another car, another car. How about this part? See, I guess there are people moving, right? It's a sidewalk. This is really Mecidiyeköy. You know this place, right? I think this is in front of the Trump Tower or something like that, right? Okay. So this is going to detect anything that moves. Okay, this is about motion detection, etc. It works very well for security cameras. Okay. Usually what you would expect is I have a background and nothing changes in my background. Anything different from my background is the objects that are moving. Okay, that are moving. So the thing is that how do I estimate the background? How do I do this? This is my background image. This is my foreground image. If I subtract this background image from my foreground image, okay, and if I, by the way, this is absolute value operation, and this is minus. Subtract this image from this one, take the absolute value, all the pixels that have a large enough value greater than the threshold means that those pixels are moving. How do you get this image? You might say that close the traffic, okay, stop the traffic, take a picture, and stop everybody, take a picture, and it might work. That's going to be very expensive for all the places. That's not going to work because even if you have this image, okay, this image changes from time to time, depends on the time of the day, right? Depends on cloudy days, depends on rainy days. During the night it's going to be different. And in Turkey, usually we know that usually our municipalities, they keep working on our roads, okay? They will make patches and everything. Okay? So how do I find this background image? Any guesses? That's the idea. I mean, that's why we are looking at these background images. Why we say it's a background image. One approach would be assume your previous image is your background image. Is it a good assumption? Let me take this out. Annotations and clear annotations. Clear all. Assume your image T-1 is your background image. See, these two images are not the same thing. I guess this one moved a little bit, right? It is moving this way. Use this color. These guys are moving this way, and these guys. See this one? This part is different than this part. So this is T-1, this is T. Right? So I think this picture is from 1990s. Is this a Shaheen? Looks like a Shaheen, right? There are no Doblos. This is not a Doblo, right? This is. Well, anyway, this is from 1990s. So, is this good? So just take your background as the previously taken image. If there is a difference between these two, it means what? That pixel is moving, right? So what is the problem with this?
We will get discontinuous things, I suppose. The middle part is not moving, so we have a bright part on the...
Consider this pixel. For this pixel, it's going to correspond to the front part of the, let me exaggerate a little bit. So the front part of the van is going to correspond to the back part of it. Their colors are, although the object moved, their colors are exactly the same. It's not going to work very, very well. You might say that Why do we have to take the previous image? How about taking 10 images before, right? 10 images before. So it's going to be a little different, but again, my background pixels might include pixels from the other cars. That's not going to work very well. So that's why, I mean, this is what happened. So if you take your threshold as like 25, take the previous one. If it is greater than threshold, then mark it as foreground pixel. Okay. If your threshold is 25, you get this, 50 this, 100 and 200. See, I cannot detect the center part of this van here, right? It's always a problem because same pixels keep coming back. Okay. Well, it works kind of. At least it's going to tell you if there is a movement or not. Our motion detectors, where do we have a motion detector? Very cheap motion detectors that you use at home. It works this way. It keeps taking the difference between two frames. If there's a difference in terms of infrared signal, it just turns on the light. Well, most of the time it fails, I know, right? It fails most of the time. Not most of the time, but many times it fails, but that's okay. This is very cheap, right? But for security applications, I mean, you cannot afford to lose 1 or 2 frames, etc. So we have to do better. Another alternative is, don't do this. Don't take this as your background image, but use a mean filter. What's a mean filter? Take the mean of, for example, 50 frames. Mean of, for example, 10 frames. So this is my background image. I took the mean of average of 10 frames. You see that man, that van is doing this, okay? Maybe if I have taken 500 images, right? 500 images and it's mean, it would have worked maybe, but that's how it works. And these are the results. And with the mean filter 20, I get this result. Well, it's getting better, right? For 50, it is this. Not bad, and I don't have that problem anymore. Remember this part of it? I don't have it still. Okay. By the way, taking the mean of 50 images means that you have to add those 50 numbers for each pixel, right? And divide it by 50. The nice thing is that I can do it in a running average way. Okay. I take the last 50 frames total, and I calculated my background image, and then what did I do? I subtracted my 50 image back from my total, and I did the new one. See, it's a running, so it's like if these are my 50 images from pixel, I know the total, so get rid of this one, add a new one. Get rid of this one and add a new one. So if I keep doing this, it's a running average, right? In real time, I can always calculate my of course, you need to keep these 50 images in your memory, otherwise it doesn't work. Okay, so there's something still. I see some smoothing stuff. Another alternative is median filter. We have seen this before, I guess. Median filter is not going to take average, it's going to take the median value. Okay, and if I take the median for 50, it's going to look much better. See? There are no smoothed out parts, okay, and my foreground is going to look much better. But median is something non-linear, and you have to keep sorting stuff. That's kind of the case here. Again, the other thing is, I mean, whatever mean or median, the other thing is that you need to come up with this threshold. What is my threshold? It is 10, 50, 20. Of course, there is a noise in the image. It has to be above the noise level, but what should it be? And sometimes maybe I shouldn't use a global threshold for each case. What should I do? We should find a solution. Some people said that, why are we taking the mean or median? Get this pixel, let's say this is my pixel. Get this pixel, okay, for the last 100 frames, get a histogram of it. This is 0, this is 255. Usually you would get something like this. Okay, this is the mean of that thing, and there is a standard deviation, right? You might say this is very useful. Why? Because you are expecting to see a pixel intensity around this mu, okay? But you wouldn't be surprised if you get something around here or there, right? So this standard deviation is going to tell you what kind of things around me is expected. Maybe if you have a noisy camera and things are changing, you might have something like this. Same mu, but very large sigma value. Okay? So, in terms of threshold, what kind of threshold you will say? You will say that my threshold is going to be 3 sigma. Okay? Or 98% of my distribution that I have observed. So for each pixel you are fitting a Gaussian distribution actually. For each pixel you are fitting a Gauss curve. Okay? So that might be a thing. Some other people say that, well, this is good if there is no cloud. I am seeing this picture when there is a cloud, and when there is no cloud and there is a rain and there is a shadowy cases. Why do I have a single distribution, Gauss distribution for this case? Well, in that case, you will have multi distributions. This is called mixture of Gaussians. Okay, mixture of Gaussians says that for the same pixel, I am going to fit 1, 2, 3, 4 different Gaussians, and depending on the cloudiness, raininess, and etc., I might use a different distribution. An OpenCV implements this case. Is called MOG, mixture of Gaussian, I think 2, MOG2. OpenCV MOG2 function will give you the background pixels of a sequence, and the number of distributions is a parameter. You can give it to your OpenCV function. But it looks like I am way out of time. I will stop at this point. Oh, this is our last lecture, right? No, it is not, because I think I have missed 1 or 2 lectures. At least I know that one of them was last week or the previous week. It was holiday. 19 Mayıs. Which one? Ramazan Bayramı. So I need to take a makeup class. So next week, this time, I am going to take the. Did I give you the attendance? No. I will take the attendance. I will hold a makeup lecture next week. I have to do that, okay? Today is what? 23rd? Şöyle bir zahmet çizgi atarız. Ya da ben anlatmak zorundayım. Güvenmediğimden değil ama güvenmediğimden esasında. Bir zahmet. Niye hatırlatmadınız arkadaşlar? Yani çünkü ara vermedim falan filan.
Ders çok sürükleyici gidiyor.
Hocam ders okulda mı olacak?
Ne? Starbucks'ta mı yapalım? Ne demek?
Online olacak diye.
Why not?
Ha, online mı olsun?
Daha iyi.
Online değil ne ya? Online. Ama dersi Ya yok online yaparım. Ben kesin gider biriniz şikayet edersiniz. Ondan sonra 2 saat dilekçe yazacağım yere. Yok da ben öğrenciye dedim ki olmaz onlar dediler ki bilmiyorum. Yok arkadaşlar gelin ya.